Can you hear me? Is that okay? Okay. Is that good? Hi, I'm Jenny. I'm a grad student at Stanford working with Risa Wexler, and today I'm going to be talking about the work that I've been doing to understand the tidal evolution of satellite galaxies using JWST observations of the high redshift satellite population. High redshift for the dwarf galaxy community, maybe not so much for everyone else, but bear with me. So as we heard yesterday, dwarf galaxies in the local universe have been very important probes of both cosmology and a wide variety of astrophysical processes. Historically, however, it's been very challenging to observe these low mass systems at large cosmological distances due to their faint nature. But now that we have JWST, we can finally see these faint companions at redshifts greater than 1 for the very first time. So the plot that I'm showing here is just illustrating the stellar masses and redshifts of some of the satellites that JWST was able to detect in JADES, and comparing that to the original HST mass completeness limits in the same field. And as you can clearly see, the little gray dots are the satellites. As you can clearly see, we're probing stellar masses that are well below the original completeness thresholds of HST, which means that we're entering this fundamentally new regime where we finally have these statistical samples of dwarf galaxies in the inner regions of their host halos at high redshift for the very first time. And this is super exciting because we can use these new data to test our predictions from cosmological models and our models of galaxy formation. But in order to do that in any kind of meaningful way, we have to really first understand the systematic uncertainties and biases that are in our theoretical models, especially given the precision of these new data. And one of the main sources of this uncertainty comes from our limited understanding of how subhalos and their satellite galaxies evolve once they fall into the gravitational potentials of their host halos. So there's this general lack of consensus, let's say, in the literature as to how rapidly this sort of mass loss occurs due to gravitational tides. So we have these modern, high-resolution, idealized simulations which predict that these low-mass subhalos can basically exist as these shrinking bound remnants for arbitrarily long periods of time, while hydrodynamic simulations, which include things like baryonic physics, tend to predict that this mass loss occurs much more rapidly. The figure I'm showing on this slide is comparing the sort of mass loss tracks predicted by a hydrosim, so that's the black dashed line, and an idealized model shown in the solid orange line. If you're not super familiar with reading tidal tracks, the x-axis here is telling you about subhalo mass loss, so it's giving you the remaining bound fraction of dark matter post-infall. The y-axis tells you about galaxy or stellar mass loss, so this is the remaining bound fraction of stellar mass. And then you can think of time as progressing along each of these tracks, so starting from the top right and going to the bottom left. So as your subhalo is orbiting its host, it first starts by losing subhalo mass. Its stars are pretty intact for a while until you get to this critical turnover point, after which stellar mass loss increases rapidly. And as you can see, the idealized model predicts that this turnover happens much later, further to the left, than the hydrodynamic simulation does. And you might think that that's all good and fine because baryonic feedback can core out your profiles, accelerate disruption, so on and so forth. But the issue is that there are a lot of confounding variables due to limitations in our simulations. So we have things like halo finder errors, where the things that are tracking your subhalos across a simulation can lose them prematurely. And there are also a large number of numerical effects that could cause artificial disruption as well. So that's all to say that there's still a large amount of uncertainty as to how subhalos respond to gravitational tides in simulations. So one of the main aims of our work was to improve the modeling of these low-mass, heavily stripped subhalos in simulations, and then to assess the consistency between our simulated satellite population and that observed by JWST at redshifts between 1 and 3.5. And then in doing so, we build this framework that can be used to constrain subhalo tidal evolution. Cool. Before I talk more about the model, I just want to briefly touch on the data that we use in this work. So the observations come from Ren Spies' 2023 paper, which uses multiband near-cam imaging in good south, as well as HST data. The simulations we use are Symphony Group, which is a suite of dark matter-only zoom-in simulations looking at host halos at about the 10 to the 13 MSUN virial mass range. In this work, we focus on massive quiescent host galaxies and their satellite systems, and the plot on this slide is just showing you the stellar masses and redshifts of the observed hosts in green and our simulated hosts. Okay, now on to the tidal evolution model. So there's been a lot of work that's shown that the evolution of a subhalo's physical properties as it's undergoing tidal stripping depends really only on the total amount of subhalo mass that's been lost. So in other words, they follow these sort of well-defined tidal tracks as they undergo tidal stripping. So because of that, we use this tidal track-based model to predict the stellar masses of our satellite galaxies after they've infallen into their hosts. So in practice, what this looks like is after our galaxy becomes a satellite, its stellar mass at subsequent times is determined solely based on the remaining fraction of subhalo mass it has left, according to the equation I have up there on the slide. And before that, it's predicted from a universe machine. So this particular form of the tidal track that I'm showing comes from the Smith et al. 2016 work, which looked at the tidal evolution of satellite galaxies or not satellite, just galaxies in general, in hydrodynamic simulations. F star is telling you the bound fraction of stellar mass post-infall. FDM is telling you the bound fraction of dark matter mass post-infall. And then F1/2 is really the key parameter here. It's the thing that's encoding like where that turnover point in the tidal track happens. And it's what's really parameterizing what I'm going to call galaxy durability. So if you have a lower value of F1/2, then this turnover point happens further to the left, and your galaxy is more durable. If F1/2 is larger, then this turnover happens further to the right, and your galaxy is more fragile. And in the Smith et al. Work, they found that their galaxies were best described with this F1/2 value of about 0.05. So that's what we use in our fiducial model. It's not guaranteed, however, that F1/2 is the same value across all galaxies, and in fact, it's probably not, because galaxies have a distribution of sizes and stellar to halo size ratios, which leads to a distribution in durability. And also, this particular form of the tidal track, like I said, was empirically determined from hydrodynamic simulations, which can suffer from numerical artifacts that preferentially heat up the stellar distributions of their simulated galaxies, basically like causing them to puff up a little bit. And this mischaracterization in size can lead to a mischaracterization of stellar stripping. Like I mentioned a couple of slides back, idealized models that don't suffer from the same numerics tend to predict lower values of F1/2. So for these reasons, we allow F1/2 to vary in our analysis between 0.001 and 0.5 to sort of explore these uncertainties. This range is chosen to be very conservative, but we expect that it brackets the true scope of what F1/2 is and is broad enough to sort of encompass the full range of disruption physics that is consistent with both hydro simulations and idealized models. Okay, so this brings me to the main results. Here I'm comparing the cumulative stellar mass functions measured from the JWST observations shown in green and our simulations. So the black dashed curves are showing predictions by our fiducial model, where F1/2 is 0.05, and the gray shaded region is showing the range of stellar mass functions allowed by varying F1/2 between 0.001, which is setting the upper bound, and 0.5, which is setting the lower bound. So within our framework, the sort of range of allowable stellar mass functions spans a factor of 3 to 4, which is really highlighting the extent of the uncertainty that gets imparted on the stellar mass function by this uncertainty in galaxy disruption modeling. It's still important to note that the data and our fiducial model are consistent to within 1 to 2 sigma across the board, although the observational uncertainties are large, so take with that what you will. Let's see. There might be a hint of redshift evolution here, where you have satellites that are less durable at low redshift and more durable at high redshift, but a lot more work still has to be done before we can really say anything about that. And then we can sort of plot the same information that's shown in these mass functions a slightly different way in order to attempt to constrain F1/2. So that's what I'm doing here. I have collapsed the first 3 redshift bins down to 1, and I'm just ignoring the highest one where a mass completeness limit is not very good. And here I'm showing the average number of simulated satellites per host that fall above 10 to the 8 M-sun in green and 10 to the 9 M-sun in purple as a function of F1/2. And then I'm also showing the corresponding observed satellite counts in these shaded bands. And so the idea here is that the intersection between the solid curve and the shaded band gives you a constraint on the value of F1/2. So I've marked our fiducial value motivated by these Smith Hydra simulations in the dark gray dashed line, and I'm also showing a predicted F1/2 value from these Irani idealized simulations in the light gray dashed line. So the main takeaway from this plot here is that the data are fully consistent with our value of F1/2, but it's also consistent with F1/2 being potentially much lower than that. So galaxies may be more durable than what is predicted by hydrodynamic simulations. Our ability to really constrain F1/2 and distinguish between these two models at the moment is limited by large observational uncertainties. But there exists a lot of data out there, and one of the next things I'm planning on doing is significantly expanding our observational sample to really hammer down some of these statistical uncertainties. And then once that's done, using this framework, we should be able to provide robust empirical constraints on F1/2 and satellite tidal disruption. So with that, I will leave you with my concluding slide and happy to take questions.
I see Daisuke and Frank.
Very nice work. Have you looked at the radial distribution of satellites?
Yeah.
Because I expect that a lot of disruption happens in the inner region where tidal effect is actually stronger.
Yeah, definitely. We have not looked into the radial distributions yet, but that's something that I plan on doing, for sure. Yeah.
Great work. But the exact modeling, so I assume you use the simulations to make predictions
Yes.
with your model?
Yes.
So 2 questions there. The observations are inside 35 kiloparsecs.
Yes.
So do you do some line of sight
Yeah,
integration
yeah.
through the halo? And how deep is that cone that you use?
We do, it's like a cylinder, basically, with the, where
right.
the length is the virial radius of the host. And then we, it's like a 2D.
Okay. Okay.
Yeah.
Have you explored how sensitive it is to extending it and making it
We
longer?
do,
There's quite a bit of infalling material that is not inside.
We account for the effect of like related structure contributing to these counts
Wonderful.
in our modeling.
And the final question was, these are dark matter only simulations,
Yes.
correct? So have you played with models that account for the host
Yeah.
galaxy and how it adds to the disruption?
Yeah, not yet, but that is also on the docket of to-dos. Yeah.
It's wonderful work. I just wonder about the orbital characteristics of the disrupted halos. So probably highly eccentric orbits disrupt faster than circular orbits.
Yeah.
Would you then predict that when you look at satellites, they should be preferentially on circular orbits because of the disruption process going on? That would be a nice prediction to test,
Yeah.
isn't it?
Yeah, I think because right now we're just using this like single tidal track thing, which is kind of like averaging over like orbital parameters. Like that's not really something that we take into consideration, but that would be an interesting thing to test for sure.
Professor Chen, please sit up, and we have time for one quick question.
Thanks for the nice talk. Do we have any constraints on the stellar distribution, maybe like SITch index, because the tidal evolution of the stellar component seems to, we were trying this out, and it seems to depend heavily on the distribution of stars.
Yeah, I don't have a plot on here showing that, but I looked at like Sirsic indices varying from like 0.5 to 8, and it does affect the tidal track quite a bit. It's interesting that if your value of f1/2 is small enough, like if your satellites are durable enough, then that actually doesn't end up making a difference. But in the case that that's not true, that definitely is something that I need to take into account when I'm modeling these things. Yeah.
I think we need to move on. Yeah. Let's thank Jenny again. Next, we